So when we're looking at redox reaction at the cell level or biochemical, we need to understand that reaction, as described before, will be a little bit more complex than the reaction, the typical reaction I gave before, right? I described in the previous videos. So remember that the previous reaction was X that has an electron, and this X, this molecule X will transfer this electron to Y, right? So we have the electron right here, and then this electron will be passed on. And we know that here this is a reduction, and then we know here that what we have is an oxidation, because there is, in this case here, there is a loss of an electron, and in this case here, there is a gain. And now we understand at this point why a gain of electrons is described as a reduction. Now, although these reactions can happen easily in a beaker and with very specific conditions, when you're looking at reactions at the cellular level, things get more messy, it gets more complicated. And in this case, we know that in a biochemical reaction where redox reactions are involved, we will need enzymes for this. These are not spontaneous, and they need to be, most of all, they need to be controlled. So we need special tools, which enzymes are, that will allow the passage of electrons from one molecule to another one right here. Now, because enzymes are involved, and because this won't allow the direct passage of an electron from one molecule to another one, we will need a special type of molecule. And these special types of molecules that will be involved in the transfer of electrons are called electron carriers. And these electron carriers are molecules that are specifically have evolved to interact with electrons and enzymes and transport one electron from one molecule to another. So what we can see here is that the electron transport molecules, or electron carriers, or actually organic molecules, are kind of complex in a way, and they will be able to accept electrons, as we can see here, right? So we see that the NAD molecule here is able to accept the electron and will be transformed into NADH. Now, this reaction here, remember that we need enzymes for this. We need an enzyme in order to be able to proceed through those reactions, whether it's a reaction of reduction or a reaction of oxidation. Now, the reason why this is called NAD, and the next word is a kind of like a mouthful, it's the reason for this is it's called nicotinamide. That's the name of the molecule here. So that nicotinamide, adenine dinucleotide. So that's why, because it's a mouthful, that's why we prefer to say NAD, and instead of pronouncing all of this here. Now, if we look at our previous reaction again, if I may, we had this here, where we have the electron that's passed on Y, right? So we have an oxidation reaction here, and we also have a reduction reaction here. So now if we throw this in the mix, and we know that we need an enzyme because this might happen at the cellular level, and so basically it's a biochemical reaction. It doesn't just happen in a beaker. What will happen here, if we want to involve this molecule here, is this, right? We will have the X here with the electron, and this electron will be passed on an NAD. So in order to do this, to transform X into X like this, so this reaction right here, basically the oxidation reaction, what's going to happen here is that a molecule of NAD plus basically, will be transformed into NADH. So by accepting electrons, it will be transformed into NADH. And then we will have this here. Now, when we go further, we know that the electron will now be passed on to Y. So where is the electron now? Well, the electron now is right here. This is the electron carrier, and the electron carrier now has the electron. So this now will pass the electron to Y. And then this will convert NADH back to NAD+. So you see here, we have an oxidation of oxidation, and we also have a reaction of reduction here, right? So in this will give us this part here. So you see here, we involved the electron carriers in this equation right here. So this is the reaction as it would happen inside a beaker maybe, or a test tube if it was possible. And this is the same reaction here that would happen inside a cell. And because it happens inside a cell, and because electrons are not freely transported inside a cell, we need those electron carriers. And with those electron carriers here, and with the help of enzymes, these enzymes will allow the passage of electrons from one to the other and the final product here. Now, the reason for this little bit here is that I want to make sure that you understand how to read your textbook and the different articles or other textbooks that you might be looking at, because what we did here is really look at the different details of these reactions, and I just want to show you a different way to look at it, a bit more simpler way to look at that. So now when we look at a reaction like this one here, it looks kind of simple in a way, but it involves two redox reactions, right? We know that. And in this case here, when we involve these electron carriers right here, if we count those reactions here, we will see that if there's two reactions here, we will have 1, 2, and then we have more reactions here. So basically, if we count them, we have 1, and 2, the two previously, so these are still happening, but also we have another one here, and then one here. So we have other 2 redox as well, and those redox reactions involve the NAD molecule, right? So we have 4 of them here. Now, when you look at this here, what we did is we broke down this reaction here into 2 different steps. Now, when you write those reactions, it kind of looks like kind of messy on a piece of paper, and it looks kind of complicated. So what we'll do from now on, and then you will see this, is that we will only write these reactions here, like this one and this one. So we will look at what is there in the first part and what is the final product. And what we'll do here is that we will look at the electron carriers, NAD and NADH, so don't forget NAD+, and then we know that they are involved. And then instead of writing the second reaction like here, what we do is just put an arrow underneath. So you will see reactions like this where you have the previous, what needs to happen, and what is the desired final product. And inside, underneath, you will have this kind of like circling pattern here where you have the electron carriers that are transformed, oxidized, and reduced as well as this reaction proceeds. Now, if we bring this into the context of glucose oxidation, remember we are starting the pathway to respiration, and we will adopt the glucose as a model molecule for this. And so therefore we will be talking about glucose oxidation. And the reason why we're talking about oxidation is because we will need to harness the electrons. We will need to remove the electrons from the glucose in order to create ATP, because ATP is our energy that the cell wants. That's the energy, the energy molecule that the cell needs for so many different processes. Now, when we look at this here, and if you remember the previous image that I showed you a little bit earlier, so we know that glucose is a molecule that has 6 carbons. So it's a C6 molecule. And we know that there are different steps with different enzymes, right? Enzyme 1, enzyme 2, and enzyme 3, etc. So there's more than 3 enzymes, so I just want to simplify things. So glucose eventually will be separated into 2 molecules that have 3 carbon, right? So we will have a C3 here, and we'll have 2 C3. So one here and one here. And so, and those molecules here will eventually be converted into a molecule that's called pyruvate. Pyruvate. And that pyruvate is a C2 molecule, okay? So what we know here is that because we break a bond here, we break from a C6, we go to a C3. So for sure here, somewhere, an electron will be liberated. And here again, because we're breaking a bond, right? We're going from C3 to C2, electrons will be liberated here as well. But because we have 2 C2 molecules, we will create two C3 molecules will create 2 C2 molecules, so therefore we'll have 2 electrons here, right? Anyway, the number of electrons is irrelevant here. Now, what we need to know is that these electrons here will be captured by electron carriers. They just don't fly and float in the cell cytoplasm. They need to be transported somewhere, right? So what will happen here is that these molecules here, not molecules, but these electrons here will connect with NAD. They will be captured by NAD+, and therefore NAD+ will be transformed into NADH, right? So that is very important here to remember that. And remember that this here is always mediated. There's always an enzyme that's involved.